Hey guys, Mr. Kyle, Myers Mathematics, and let's just jump right into it. So today I want to talk about parent functions, and maybe you've heard of these before, but basically they're parents. So a better way to think about it, because that's the title, is like great grandparents. Okay, so I'm going to kind of paint a picture here for you. Great grandparents. All right. So I'm not very good at drawing people. I'm just gonna draw a stick figure. We're gonna pretend this is like a, old grandma. She has a lot of bushy hair here. Her hair's up, all bushy. So great grandparents, when you think of like a really, really old person, like they're in their 80s, 90s, reaching three digits, then they lived in a time that was much more simple, right? So think of like somebody that's really old. They're like, back in my day, we had two sticks, and that's how we played baseball, and a rock, two sticks and a rock. So, so they are simple, right? So when you think parent functions, think simple. Then you have the, child functions, the baby functions. And as, your great grandparents have kids, then you get to grandparents, grandparents, right? Where they kind of know a little bit more about the technologies of today. They're a little more astute. So they've got some glasses here, right? A little more astute, but they're still a little older, and then parents, mom and dad. So as we go down the list here, they get more and more complicated. So your most simple version is the parent function. So an example would be x squared, right? X squared, pretty simple. But then if I add 1 to it, right, it's a little less simple. It's not a parent function anymore. And then I could make it even more complicated if I add a 2, or technically here, multiply by 2. So like 2x squared plus 1. And then you have, kids. So you and me, we have parents. So maybe I'll draw a little smaller here. So little kid, you know, and there we go. So something like that, and they could be really complex or just kind of complex. So if I wanted to add a little bit more complexity to this, I could maybe say x plus 1 squared plus 1. So now it gets a little bit more complex as I go. So the most simple that it could be is the parent function. And then as you do transformations to the graph, which are the 2 and the 1 and the 1, it becomes more complex, and you have to do more things to the graph to get it to look like what you want to when you go to graph it. So before we do some examples of parent functions, let me talk just a little bit about how to identify them. So let's look at another example. Let's say I have 3 times the sine of x plus 1 over 2 minus 5. Okay, so the two things, and I'll type this out, the two things that you need to look for in order to identify the parent function, right? So to identify the parent function, here's what you need. One, you need to find the x, okay? Or whatever variable they're using, but it's most likely x because normally your parent functions, you're graphing them on the xy plane. So, like 9.99 times out of 10. You're looking for x. Find the x, and then find out what's happening to the x, okay? And I need to be a little bit more specific with this. So this doesn't include adding, subtracting, multiplying, and dividing, in which there is not a symbol for, except for maybe this. So add, subtract, multiply, divide. Anything that's like four functions, if you're familiar with that term, anything four function-y, plus, minus, times, divide, any of that stuff that's happening to x, you can ignore it. You're looking for other things, okay? So we're looking for squares, or I should say exponents, which would be squares and square roots, trigonometry, which is what I'm doing here in this case, 3 sine of x plus 1 over 2 minus 5. So the sine is what's happening. That's the thing. That's the parent function that creates the parent function. So exponents, trigonometry, etc. There's a bunch of different examples there. And that's pretty much it. So actually I'll add one more thing. So just look at the x and what's happening to it and isolate. Ooh, isolate. Okay. So going back to the stylus here. So I'm going to ignore all the other numbers. I'm just going to look for the x. There's the x. Step 1 done. What's happening to the x? Sine of x is happening, right? So yes, it's being added to 1, it's being divided by 2, there's a minus 5, there's a times by 3. None of that stuff matters when you're trying to find the parent function, right? So in this case, it's just sine of x. Boom, done, right? So the parent function, so sine x is the parent function. Sine x is the parent function. Okay, so that's one example. We'll do one more example real quick. So let's say the cube root of 3 minus 2x over 5 plus 7 times negative 12. I don't know, just making numbers up. So step 1, find the x. Okay. Step 2, find out what's happening to the x. Cube root. Okay. Times it by 2. You're technically adding 3. You're timesing it by negative 2, adding 3 to it, dividing by 5. None of that stuff matters. That's all four function stuff. So the parent function is the cube root of x. That's it. Parent function is the cube root of x. So if you can identify what the parent function is and just kind of have an idea of what the parent function should look like, then it makes it a lot easier when you're trying to graph a transformation of the parent function. Okay, so now that we've done that, let's look at what a couple parent functions are. And these are important to know what they look like. So I'm going to go back to black here. And I'm just going to look at a couple different ones here. So the most basic parent function is y equals x. All right. So here's my graph. Here's what it looks like. Goes right through the origin, up 1 over 1, slope is 1 over 1. And there you go. There's your most basic parent function. That is the parent function for all line graphs. Okay. With maybe the exception of like x equals. It's sort of its own classification, but it's a line. So this is the parent function of pretty much all line graphs. Can't talk. Line graphs ever. And let's just kind of go by square, and then we'll go to cube. Spoiler next. So if I do this, and by the way, the arrows pointing up into the left and right, those are just my x and y axes. So the x squared, that's a classic parabola, right? Which normally looks like a u unless you multiply it by -1, or if you have a parabola flipped to its side, but then it wouldn't be a function. So there's my parabola, right? Anything with x squared in it is going to look like that, like a u. Could be stretched out some more, or it could be skinnied up, a little bit more skinny. Could look like that. Or you can move it around, right? It could be over here or over here. And then, of course, you can flip it. So you can flip it around and move it over too. So it could be flipped like that. But y equals x squared is a parabola with its vertex at the origin. Right? I'll kind of make that a little bit more highlighted there so you don't get it confused with all the other little ones I just drew. And I'll do one more. So these kind of just keep going continuously forever. But you'll notice kind of a pattern as you go up in degree if you ever graph this on a graphing calculator. If you use Desmos, Desmos.com, it's a free graphing calculator tool. You can actually just kind of explore what's going to happen as you go up in powers here, but basically you just start to see a pattern. So x cubed kind of looks like a little, like a kind of like an S a little bit, or like half of a parabola and the negative half of a parabola stuck together. So it looks something like that. A little bit S-like, and then again, kind of like two halves of a parabola where one got flipped over. And then of course you can move that around too, right? But then that would be a transformation or a child of the y equals x cubed graph. So I can keep going up, y equals x to the fourth, y equals x to the fifth, so on and so on. But those are pretty much the only unique ones. It doesn't really get any more unique after that. It just kind of repeats. There's like a pattern going on. So you can pretty much end at y equals x cubed. So y equals x, line. Y equals x squared, parabola, U-shaped thing. Y equals x cubed is the S or the snake-shaped thing. Okay, so now let's get into a couple different areas. One being y equals the square root of x, which actually is basically just a parabola flipped on its side. So if I were to square both sides, I would get y squared equals x, which is basically the flip side of y equals x squared. So when I say y equals the square root of x, it is very similar to a parabola. Now, since I didn't put a negative in front of the square root of x, it would only be the positive version of this. This negative version down here to make the full parabola doesn't exist unless I put a plus or minus on it in front of the square root of x. So just the top part, just this part right here, is actually the only part of the graph that exists for y equals the square root of x. All right, so then I have y equals the cube root of x. And again, after I take the cube root of x, if I were to do the fourth power of x or the fifth or sixth, it just starts to repeat again, just like the parabola and the cubic and all that. But funny enough, when I do the cube root of x, I actually kind of get an s, but it's a full-on S-shaped thing, but just flipped on its side. So it's actually kind of look like this a little bit. And the reason why is because I can take cube roots of negative numbers. X can be negative in this case, whereas in y equals the square root of x, x cannot be negative. I can't take the square root of a negative number, not in the real number system. But I can take the cube root of a negative number. For instance, the cube root of -1 is -1, because -1 times -1 times -1 is actually just -1. So, oops, sorry, +1 and -1 make a -1. So you just end up with a full-on graph for y equals the cube root of x. And of course, as you go to y equals to the fourth root of x and so on, each even root is going to have the same issue. You're going to only have half of the graph of a quasi-parabola looking thing. Okay, so that's that one. Let's switch back to black here and talk about rational functions, y over x, or sorry, y equals 1 over x. So for this one's really important too, because it's basically the dad, the father of all rational functions, and it looks something like this. And actually, I'm going to use two colors for this one because I need to make this a vertical asymptote. Here's my vertical asymptote. It's on the y-axis, and the x-axis is a horizontal asymptote. So there's two asymptotes going on here, and the graph kind of looks like an L, right? So this is basically an L, and it kind of approaches these asymptotes. They're like guiding lines to graph our thing here. So asymptotes are going like that, and it's approaching them. And then I also have one over here in the negative area, which is kind of like an upside down, flipped over L, like the L on Waluigi's hat, if you're familiar with Mario. So I have the Waluigi over here, and the regular L for Luigi over here. So it's a Luigi and a Waluigi. Right, that's how you can remember that one. Luigi and Waluigi. And then you have one that's really similar, which would be y equals 1 over x squared. I'm not going to list that one because it's kind of the same. It just flips this guy over here, so it's kind of like that. For y equals 1 over x squared. So I won't really talk too much about that. I'll just go straight into a couple trig functions here. So it's good to know y equals sine of x, which is very similar. It's very similar to cosine. So y equals sine and y equals cosine are both wave functions. They're very, very useful for describing waves. So sine starts at the origin, and it does a wave. Right? So it looks something like this. And this is not a very good drawing of it, but you kind of get the picture here. It just keeps on going forever, and it just never approaches, it doesn't have any asymptotes or anything, and it never is going to approach the x-axis, kind of level off there, because there's no asymptotes to make it do that. It just kind of goes on forever and ever, just in a continuous wave. And cosine is kind of the same. It just starts up here. Cosine starts up here, and then just does the same thing as sine, right? And then tangent, we'll do tangent, y equals the tangent of x. Tangent's really interesting because it is similar to sine and cosine in that it's kind of wavy, but it also has asymptotes. So it's kind of very similar to a cubic function, like y equals x cubed, in that it looks kind of like this. But it's not quite the same. It's not exactly a cubic function, right? Sort of like you know, when somebody at the mall dresses up like Santa. It's like sometimes they look a lot like Santa, but they're not Santa. So this graph is a mall Santa, whereas the real Santa would be back up here with my y equals x cubed graph. So notice y equals x cubed and tangent of x look very, very similar right now, except tangent x has asymptotes, so it doesn't go on for infinity. This one little piece right here does not go on for infinity to the left and to the right. It stops. This little piece right here stops at negative pi over 2 and then at pi over 2 on the right hand side. But it does keep going forever with just little breakpoints where it can't equal a certain thing, and it kind of just is an infinite number of little cubic functions. So it's sort of like if you took a bunch of cubic functions and just spliced them all together and it just keeps going. So it just kind of looks like this. It just keeps going and going, like the Energizer Bunny, forever and ever. There's an infinite number of the cubic function looking things that make up tangent x, and it just never ends. Okay, and then of course it's similar to cotangent. Okay, and then last one. So this has to do with sine, the inverse sine, or sorry, the reciprocal of sine and cosine. So cosecant and secant. And actually, you build these off of the sine graph and the cosine graph. So y equals, last one. That was a terrible y. There we go. y equals, let's say the secant of x. So I'll write this off to the side. Secant of x is equal to 1 over the cosine of x. That's just a trig identity that we should know. So it's going to be built off of cosine, right? So I'm going to do a graph, and I'm going to do kind of a dotted thing for cosine. So cosine starts right here. Kind of mentioned this earlier a little bit, but it looks something like this, right? It just continues forever. So it's not an asymptote per se, but it does help us to build our secant function. So at the tops and the bottoms of our cosine graph, we actually have like parabolas, parabola-like things. And they're not quite parabolas because they also have actual vertical asymptotes. Every time the wave, the cosine wave that it's built off of, every time the cosine wave turns around, starts to turn around, it's actually called a point of concavity. You'll learn later on in calculus, or if you're in calculus now. But right when the wave starts to turn is where we have vertical asymptotes. So all these little vertical asymptotes are happening. Go up like this, down like this, and there's just an infinite number of them. They never stop. So there's just an infinite number of vertical asymptotes at all of the turnaround points. All of these points right here. It doesn't have to be 0 necessarily, because again, you could move the graph around. You can transform these graphs, but it's right at the turning point of where the hump is a hill, and where the hump is turning into a valley. Right at the turning point from hill to valley. That's where the asymptote is, and then you take the absolute top of the hill and the absolute bottom of the valley, and those are like parabolas. And again, it's kind of like Monsanto's. It's not really a parabola, because a real parabola would be x squared, and we don't have x squared, so it's not really a parabola, but it's very similar to one, because it looks just like it, except that it is guided by these asymptotes here. Right? And there we have it. Those are some of the most important parent functions to remember. Okay, and I kind of did them in order of importance, starting with most and kind of going towards least. Not in like a for sure way, because I do think some of them could be more important than others, and I didn't do them all precisely in order. But anyways, you have y equals x squared, y equals x cubed, right? The big three. Then you've got some root graphs, y equals x squared and y equals cube root of x here. And then y equals 1 over x squared, very important, your rational function, parent function, right? So basically all rational functions come from that. And then you get into your three, I should say, three unique trig graphs. The sine graph, which goes similar to cosine, the tangent graph, which is similar to cotangent, and the secant graph, which is similar to cosecant. Okay, so I forgot to write that actually. Similar to cosecant, which is abbreviated as CSCX. All right, so that is all I have for you guys today. So again, this is important, because if you know the parent function, then when you actually get to identifying the parent function and figuring out how to graph it, all you need to do is say, okay, I know what this should basically look like. Let's graph a few points, and I'll be able to get it from there. Okay, it makes your algebra stuff a lot easier. So I'll do another video on that in the future, just exactly how that plays out. But this is what parent functions are. So this was meant to answer that question and give you some examples. And I hope that it did, and I hope that it helped. Throw a like if this video was helpful. Subscribe if you want to see more videos like this. Throw a comment in the comments below if you want to see any other videos. Or if maybe there was a parent function that I missed that you think is also really important. I know I did leave a few out on purpose, just because I didn't want to go through every single possible parent function that was out there and just kind of hit on all the ones that I thought were the most important. But if I left one out and you thought it was really important, just throw that in the comments too. And yeah, so this has been Mr. Kyle at Myers Mathematics. And hey, so on my website, myersmathematics.com, I have a free guide. It's essentially meant to be a guide on how to not miss any more math mistakes. So if you're in school and you're missing problems, your problems can all be narrowed down to 5 things. So I have a guide. It's the 5 math mistakes everyone makes and how to avoid them. All math problems I've narrowed down to 5 different things. So I want you to download that free guide. You can grab it from my website, myersmathematics.com, and just give it a nice read. And then afterwards, all you need are just the 5 pointers, which I laid out really specifically in the guide, and the simple solutions to each one, which are kind of explained in more detail in the PDF guide. All right, so go grab that. It's at my website, myersmathematics.com. And until next time.